Good evening, ladies and gentlemen. Welcome to the inaugural lecture of Prof. McGregor. Can I please ask you to rise as we welcome the procession inside the venue? Thank you.
Right, good afternoon, ladies and gentlemen. You may be seated. Right, so for those of you who don't know me, and also for the colleagues online, my name is Wikus van Niekerk, and I'm currently the Dean of the Faculty of Engineering. And this is a very historic event, because not only is it Professor Craig McGregor's inaugural lecture, it's also the first time that we are hosting an event in this beautiful room. So thank you very much to the university for providing such a beautiful venue to the Faculty of Engineering. So I'm going to start by welcoming, and I want to welcome Professor Nicola Smith, our acting Chief Operating Officer. She's also the person that signed the check for this, so thank you very much for signing that check. Professor Sibusiso Moyo, the DVC Research, Innovation and Internationalization. Dr. Runel Retief, our registrar. Also Professor Guy Mitchley, the Director of the School for Climate Change. Professor Christian Skreefe, our acting Vice Dean Teaching and Learning. Professor Johan van der Spey, who is the Chair of the Department of Mechanical and Mechatronic Engineering. And of course, our guest of honor, our honorary speaker, Professor Craig McGregor. I also then want to welcome Gilles, the partner of Professor McGregor, and specifically his parents, Ian and Marief McGregor. Thank you very much for coming down here and sharing this wonderful occasion with us this afternoon. And then also for our colleagues from Agua Power, and you'll hear later why they are very important, who are online. Thank you very much for attending online. And then we have quite a number of colleagues from the Department of Mechanical and Mechatronic Engineering and also other departments. We have friends, we have collaborators, students, and all others attending in person as well as online. So now you are all welcome. So I also have to make some procedural arrangements here. So there are bathrooms on the left. If you go outside there, but there's also, if you want to sneak out the back, there is also some bathrooms there. You need to put your cell phones on silent or off. And of course, you can evacuate when the alarm goes off either through that exit or to that exit. Just make sure that it's safe. And if that one is blocked with smoke and fire, rather use the one on that side. So those are all the formalities. So my next task is to introduce Professor Craig McGregor to you. So he is a professor in the Department of Mechanical and Mechatronic Engineering at Stellenbosch University, where he holds the Agua Power Chair in Concentrating Solar Power and leads the Solar Thermal Energy Research Group, also known as STERG. His research spans concentrating solar thermal systems, thermal energy storage, green hydrogen, and energy systems engineering, with a focus on the role of solar thermal technology in South Africa's energy transition. Before joining Stellenbosch, he had a long career of 20 years at Sasol, where he led the South African development of the Stelio heliostat. And for those of you who don't know it, that Stelio has nothing to do with Stellenbosch, even though we would like to think it has something to do with Stellenbosch. But it's a little lizard, if I'm correct, right? So it's a little lizard. That's where the name Stelio comes from. And it was done in partnership with a German engineering company, SBP Sonne, And Stelio won the Solar Paces, and Solar Paces is where everybody who can spell CSP and know that it stands for Concentrating Solar Power gets together once a year at the Solar Paces Conference. It's the most important conference in this area, and there they won the Innovation Award in 2015. And not only that, it has also been commercially deployed in China. So they're actually using the Stelio heliostat in China. At Sasol, he also led 2 chemical technologies from the development through to commercial operations. And I think for us as a Faculty of Engineering, it's key that we can bring people with extensive 2 decades of industry experience back into the academia. So Craig, thank you very much that you made the sacrifice to come and join us. But I know that it's a real pleasure to work in this faculty. So currently the work at Sturk draws on operational performance data from the Bokpoort and the Redstone CSP plants, again thanks to our partners at Aqua. His group research addresses CSP cost reduction, grid integration modeling, and the economics of long-duration thermal energy storage in the South African context. Since joining Stellenbosch, he has supervised over 40 postgraduate students and postdoctoral researchers. He has a particular interest in how engineers learn to work effectively with artificial intelligence. So he has 2 other big friends, one called ChatGPT and the other one Claude, and they have done a lot of work together in this field. And Craig, if you want to hear more about AI, you're not going to talk about AI today, but if you should speak to him afterwards. He really is helping us a lot in our own journey on AI and integrating that into engineering education. So Professor McGregor also received the Bill Neely May Gold Medal from the South African Institution of Chemical Engineers, which is awarded for contribution to process technology. His work has been published in a host of different journals, including Solar Energy, Journal of Energy Storage, and Energies, among others. Craig? It is really an honor to have you on our staff and a privilege to be here this afternoon to come and listen and now I'll say what everybody says, how you're going to profess to us what you are doing, since you are now a professor. Thank you very much.
So with an introduction like that I wrote myself, I think that's half the talk done already. So thank you, everyone. Thank you particularly to family, to colleagues, to the Stellenbosch University Rectorate. It's great to have everyone here. And thank you to the Dean for actually getting me here into Stellenbosch, where I think it's been a fantastic time. So my talk today is not even up there, so.
I think you may just wake up the computer. Ask ChatGPT.
Claude, please turn on the screen.
There we go.
I mean, I was up there even when I was sitting there, and now it's disappeared. So, sorry. So, the talk is titled Sun, Steel and Storage, and we're looking at solar thermal. So solar thermal, from the introduction you've heard, is obviously my passion and its role in the energy transition, and particularly in South Africa's energy future. So Vickers mentioned the Stelio heliostat. So this is actually what Stelio looked like. So this was something that was conceived when I was working in Sasolburg, and Sasol decided it wanted to get into solar thermal, and so we found SPP Zona, which was one of the top companies in the space who was working on solar thermal, and we came with him and we said, we got some ideas on how to make a great heliostat. And so we went through this whole design phase. The mechanical engineers in the room will know exactly what these things are. We went through let's see, I'm not allowed to walk away from here. Laser pointer. Let's do that. Laser pointer. So through a phase of wind tunnel testing, eventually it was built as a prototype that was then tested in southern Spain and performed absolutely fantastically. And then Sassel said, well, we're changing strategic direction and we're going into the US. There's a fantastic project in Lake Charles. We're going to do that. Another talk. And so SPP Zona took the Stellia heliostat into China. As Vickers says, it's actually named after a little lizard that sits in the sun, and that's the reason why it's called Stellia. But South Africa hasn't done this. So a bit of the question is why? So part one of the talk is about the sun. So South Africa has a massive challenge. 80% of our country's electricity, that's about 180 terawatt hours, all comes from coal. That coal was built in the 1970s, the 1980s, and those plants are now 50 years old, and they're at end of life. And we know what problems this causes. We've been through load shedding. I see some head nods up at the front there. So it is critical that we replace this infrastructure. So the picture on the right is the Tutuka power station. So that's a 3.6 gigawatt power station, and they're all about 4 gigawatts each of these power stations. So we've got about 6 of them that we need to replace in the next 20 years or so. It took us 20 years to build the Kusile and Medupi power stations. So we've got to do 3 times that, and we want to do this now in a way that uses the cheapest energy sources and the cleanest energy sources, and certainly just on price, renewables is that cheapest source. So everybody here knows that South Africa has great sunlight, but you might not know that we actually distinguish 2 different types of sun. So the one is called beam irradiance. That's this one here. That's the sun that comes straight from the sun. And shout out to Aaron who drew this very nice diagram for me. And then there's diffuse irradiation. So that's the one that gets diffracted off the sun, or if there's any dust in the sky. So different solar technologies, particularly photovoltaics or PV, and solar water heaters, so those are the typical ones you get on your rooftop. They can use diffuse light. The advantage, though, with direct or DNI is that you can concentrate it. So anybody who's had a magnifying glass and as a kid and chased after ants or worked with leaves knows what you can do with concentrating light. So we can get up to high temperatures, and when we've got high temperatures, we can do stuff with it. So the map on the right is a map of the beam irradiance, so solar resources, and you can see South Africa is there here in this dark red area here, and the only place that's better is this little spot here up the top of the Andes Mountains, which is the Atacama Desert. A lot of solar thermal power, CSP, has been built in Spain and near the Gobi Desert in China. And you can see our solar resources are much, much better than they are. So this is an opportunity for us. So how do we use that sun? There are 2 different ways we can use and concentrate sun. So the first is we can concentrate it in a line. So if you remember some of your mathematics, a parabola shape lets you concentrate at a single point. And so if we build these parabola-shaped curved mirrors, we can concentrate the sunlight up onto this tube here, which is we can pass a heat transfer fluid through, and we can concentrate that heat up to about 400 degrees Celsius. So that's way hotter than your solar water heater does on your roof at home. And that's sufficient to generate steam and drive a steam turbine. So we have 4 plants in South Africa, 4 concentrating solar power plants that use this parabolic trough technology. Those are the Bokpoort, so that's one of the aqua plants. The Kachu, the China, and the Alanga plants all use this particular technology. We can go one step further and actually concentrate, instead of along a line, into a single point at the top of a tower. So here now we've got laser pointer again. We can concentrate there, reflected off a mirror. These mirrors here are called heliostats, and that's what stereo is. So these focus the sunlight up at the top of the tower there, and we can get to much hotter temperatures by concentrating at a single point. So this is the equivalent of the magnifying glass. So this is actually a photo of one of the Sturg trips. Some of the students can actually, you can see reflected as the image in the mirror there. So this is the Redstone plant. It's another of one of Aqua's plants. It's a 100 megawatt central receive or tower CSP plant. Who here has even heard of this plant? Well, the CSP students and some of my colleagues. But not many people even know that this resource, this technology has been built in the country. So just to kind of go through how all of that works then, so how do we get from that heat to electricity? So we start here with the sun. Our heliostats track the sun and concentrate that sunlight up at the top of the receiver. We take our heat transfer fluid, in this case it's a molten salt, that we pump up into the tower. There it gets exposed to that concentrated sunlight and heats up to 565 degrees, and then we put that material into this hot tank. So during the day we're pumping the cold tank down and we're filling up the hot tank. So we've got at the end of the day a tank full of hot fluid that we can use to generate electricity at night time, and that's what allows this CSP technology to get 24/7 power. So that's right through the clock. So to complete the cycle, when we want to generate electricity, we pass the hot molten salt through a series of heat exchangers. That gets put in contact with boiler feed water, high purity water. We generate a high pressure superheated steam that goes into this turbine, that spins the turbine, and that turns the generator, and then we get our electricity that goes into the grid. Our exhaust steam then gets condensed and recirculated so that we're not using up water in the system. So South Africa has a whole fleet of these that we're pretty much unaware of. We have 600 megawatts of CSP, both, as I said, the trough and the tower plants. The latest one, the Redstone one, has enough storage to get 24/7 generation. You can see here on the right a map involving one of my students. We're looking at where do we locate future CSP plants and how can we balance the grid. So you can see here the grid network and of course the solar resource as well. So these 7 CSP plants have totaled what's equivalent to 85 billion rand of investment in today's money. So it's a significant amount of money that's gone into this, and really demonstrates that this technology is bankable and can be deployed at scale. So the next part, we will ask, well, what does that mean for South Africa? So steel. This is a projection that comes from IRENA. So IRENA is the International Renewable Energy Agency, quite a mouthful, but they're one of the best in terms of predicting the deployments of renewable technology. So they're quite a good source. And they looked at both the potential of the technology worldwide, so that's shown here, as well as what it could mean for South Africa. So I'll get to that on the next slide. So at the moment, we've got about 6 gigawatts of capacity installed worldwide, of which South Africa has 600. But they see potential by 2050 for nearly 1 terawatt of installed capacity. So that's a gigawatt. That represents, if this comes to pass, nearly 800,000 jobs, and would require about $2.5 trillion in investment to do it. So there's a lot of potential. Well, there's a lot of stuff that has to go into lots of money to build renewables that we need to commit to. If we break it down and we look at the materials that sit in those two plants, so this is from that same IRENA report, looking at solar towers and parabolic troughs, you'll see that most of the material is concrete, it's steel and iron, it's the glass that goes into mirrors. And these are all things that our industrial base, our manufacturing base in South Africa is set up to do. So through this program, particularly those existing plants, around 40 to 44% of that value, that 85 billion has stayed in country and has been invested in country. And there are a number of suppliers that work in the space that are actually South African companies mentioned in this IRENA report. And of course, there's a lot of potential for additional capacity to be localized. Now, if we compare that against our other sun technology, which is photovoltaics, both of them, when you look at the renewable energy procurement program, have achieved about 40% local content. But when you look at where that money is going, it's going into quite different things. So on concentrating solar power, it's going into piping, steel structures, heat exchangers, tanks, etc. That's what our industrial base is set up to manufacture. And that IRENA report says we can go, as South Africa, up to 60%. So there's a lot of potential to expand that. When you look at photovoltaics, a lot of the money sits in PV cells. And PV cells get manufactured in China. That's just a fact. Europe and the United States, which used to have their own industry base, have all exited that market. And when we say with PV that this is 40% local content, that's actually imported Chinese cells that get repackaged with some glass and aluminium and get called a local product. So there is some accounting that's going on there. So I'm not trying to put down photovoltaics. It has a very important role in our energy future, but I want to show that CSP has potential for local value creation and job creation. So back to Stelia. So you now know what a heliostat is. It's something that tracks the sun. So these are things that our automotive industry could make. They steal, they have drives that matches our local manufacturing base. As Vickers said, it actually won the Solar Paces Innovation Award, and it's considered now the best or the gold standard for heliostats. So it's quite something to be associated with this. So when any of the reports look in CSP look at heliostats, Stelia is the benchmark. It has the lowest cost of any commercial heliostat. It also has the the best optical efficiency. But what they don't tell you in any of those reports was when we set out to do this project, we set out to make a South African project, a South African product. This was something that was designed to be manufactured and designed and manufactured locally. So that was our starting point. So we did all this great work, but it's China that has gone and deployed this technology and not South Africa. Part 3. So part 3 is about getting solar power at night. And to talk about that, we need to talk about storage. And if we're talking about storage, obviously all of the economics come in. So I showed you originally what a normal CSP plant looks like. This is what modern CSP plants look like. Included on the right here are a whole bunch of photovoltaic panels. And the purpose here is to combine the best of the two technologies. So we've got a hybrid plant that has really cheap electricity from PV, but that only works during the daytime when the sun's shining. But we have the solar thermal with storage that can keep the plant running at night. And the advantage here is we can use one single site with common infrastructure, one grid connection, all of it working together. So this is the kind of configuration that's being built now. Dubai has a 1,000 megawatt field that includes solar thermal and PV together. And of course, you can extend this to wind as well. So you might be asking, but Prof. Craig, why don't we just use batteries? So here's a comparison of the costs of the two different storage technologies. The first is the molten salt, which we can build for a system. So the system here includes the tank, the pumps, the molten salt itself, for about $20 per megawatt hour thermal of storage. Battery energy storage, or BES system, so we're talking about the system now, not just the battery cell itself. So that includes all the other things you need for a battery storage. You can't have the batteries blowing up because they're too hot, so they include air conditioning, they have inverters and everything that connects them together. That costs about $200 a megawatt hour. So about 10 times cheaper, so storing thermal energy much cheaper than storing battery energy. So whereas with a battery energy storage system, we typically limited to 4 hours of storage. With salt, we can get up to 16 to 20. So on the costs, you can see here photovoltaics comes in at around $35 a megawatt hour. So that's just for the PV cells themselves. But that just gives us energy when it's when the sun's shining. We actually want what we call dispatchable generation. So that's when we switch on the light bulb, the light switch, we want the light to actually turn on. So the US here include what they call a cost of firming. So this is their method. So the one here I show is for Texas. So that's actually the cheapest. So in Texas, they have very cheap natural gas that they use to provide backup. And that takes that cost of PV, a firm PV system, up to $77. CSP here sits at 95. And if we compare with our batteries and now 12 hours of storage, which is enough to get us through from 4 p.m. through to 8 a.m., so that's through all the hours at night, we're at $166. So CSP, much cheaper than batteries and PV. And then the final one I include is nuclear. So nuclear is clean. It's depending on your definitions of clean. But it's the one that actually appears in our integrated resource plan, which is the company's plan for electricity. So using some relatively trustworthy figures, so in this case I've used Lazard's, the cost is $140 a megawatt hour, but that's kind of your best go. When in the West, typically there's two cases. There's the Hinkley Point in the UK, there's Vogtle Power in the US, and both of those have gone through 150% overrun. So that means the plant actually cost 2.5 times to build what you planned for financially. And that takes that number there up to $229. So nuclear, way more expensive than CSP. This number down here is what the South Africans assumed when they developed the IRP. Interestingly, that's the same number as what the Chinese are building CSP for at the moment. So CSP, the cheapest option to get dispatchable generation. So we can use that in a grid made up mostly of wind. So this is a typical South African grid profile. So low demand in the evenings, there's a morning peak, drops through the midday, peaks in the evening, and then drops through night again. So we can build a renewable grid that has mostly wind. To fill up this midday peak, we add some PV. Batteries here, we charge when there's excess solar, and that's deploying into the peaks. So that's the purple. And we've got solar thermal here running in that day and night, through the night through to the morning. And the advantage here, because it's dispatchable, it can match with the wind and the PV resources as they move through the day. And just in case it's not windy or sunny enough, we've got some backup as well. So this is kind of the getting to the end of our story. So why are we not building lots more CSP plants in the country? So this is some other research that we've worked on. The green here looks at the prices that went into the renewable energy procurement program through the 4 bid windows where CSP was procured in the country. We have this strange thing where we have a bid window 3.5, which not many people know about, but that was a special bid window that sat between bid window 3 and bid window 4, and that was only for CSP. The maroon line here, that's the international prices for CSP at the same time. So you can see we are coming in cheaper. This is being corrected to South Africa with the rand-dollar exchange rate, also using South African weighted cost of capital. So you can see we can manage to get in lower. We successfully did 600 megawatts of that, but at the end of bid window 3.5, CSP disappeared from our program. And if you go and delve into the documents, you see what they actually did in the planning was they compared the $35 or the $37 for PV against the $95 for CSP, and they said, well, PV is cheaper, we must pick that, but not accounting for the fact that you actually need to compare them on apples and apples comparisons. You can see where China is now. That's just over Rand 20 a kilowatt hour. Compare that with what you're paying at home to your meter. So, what do we do about it? So, we're trying to work on that problem here at the Solar Thermal Energy Research Group. So, we've got 3 things we're really trying to target. So, the first is, what can we do about manufacturing, and how do we close that gap with China? Can we get down to the 1 rand, the 1 rand 20? We've got our sunroof lab here, where we try out different things in the technology-wise. We're looking at how do we use CSP in the grid and what role can it play. So here's some of that research I mentioned earlier on. Where do we site plants? And you'll notice that outside of the Northern Cape, where we've traditionally put plants, there's some nice areas here in the eastern side of the country where you sit in the summer rainfall, and so you get some nice solar resources in winter when you've got less hours of sunlight. And then there's some nice places as well in the Western Cape that sit on the grid backbone that we have. And our final thing is through the Aqua Chair, and thank you again to Aqua for the kind sponsorship. We're looking at how we take that data for the operating plants and how can we improve the performance of those plants and get better CSP technology for the future. So to conclude, we have fantastic solar resources. Few other places in the world can match that. CSP matches our industrial manufacturing base. It's steel, glass, and concrete. And we can do this more than, we can industrialize more than any of the other renewable technologies. And we get really cheap storage when we do thermal LNG storage, and that lets us get to dispatchable generation. So that we have the resource, we have the industry. So I would like to propose that it's time to rethink CSP in South Africa. Thank you very much. And I should let you know, I forgot to start the timer, so I don't know how long that took. But I'm happy to take any questions. Thank you very much. Hi.
2 questions. First one is,
First question, what's the potential for linking a CSP hybrid plant to a data center if you're far from the grid? Is that something that could really turbocharge South Africa's contribution to AI revolution? Seeing as you're also an AI expert. And what is the vulnerability of these systems to an extreme weather event like a high wind, tornado type thing, or hail, a hail event?
So that's 2 very good questions. Thank you. Thank you, guys. So the first question is around data centers. So my expertise is teaching students to use AI responsibly and not data centers. But I think that's a fantastic opportunity. Data centers very much are energy hogs. It's well-known problem, and the deployment in the United States is facing challenges because there's just no electricity. So I think there's a fantastic opportunity here in terms of remote lands where you can put data centers with dispatchable power next door. The second question was around extreme weather events. So the first is there's a lot of design thinking that goes into the weather. So the first thing is they have specifications on the glass to be weather resistant, and to actually test the glass, they basically make an ice tennis ball and shoot it at the glass and test them. So the glass is supposed to be hail resistant. The second thing is you asked about is the wind, where there are 2 things they do. They have they move the structures, whether it's a trough or a heliostat, into what they call a stow position, whereas where there's the least wind resistance. And then these things get designed for hurricane level wind. So the structure still has to meet all of the design codes for buildings in the country. So it, obviously, if you have an extreme event, things could happen. But over there has been one case of weather damage to one of the CSP plants in the country. And that was on one of the trough plants, and it was only the very outside edge of the plant that got damaged.
The shape of the reflector painted
Why is it a
shape of the reflectors, size of pentagon shape.
so why is the stereoheliostat is a pentagon? So you would in some of the other images, the normal ones are typically rectangular. But when you've got a rectangular form, you land up with rectangular support structures behind it, and they're not very rigid to changing positions relative to gravity. So as you change its position, as you're tracking the sun, they deform. But if you have the radial spars, that's much less susceptible to the change. So ideally you want a circle, but that's quite hard to build with glass. So we went through and we checked 5, 6, and 8-sided, and 5 happened to be the cheapest with the best optical performance.
Hi, Prof. McGregor. Thank you so much for the interesting presentation, just being able to see where your research comes from, and just the, the reach of it, and also how relevant it is to our country. So I actually want to ask, in terms of the investment that you're speaking about, I think your presentation alluded mostly to scale, like full-scale implementations for sites that would, it seems like they're really large. I was just curious, because I think a lot of people in the country are trying to get off the grid to be sustainable, or self-sustainable. Is there, I've also seen some projects where students are cooking pointy pots with the mirrors. So I'm just curious if there's like a scaled version that could be maybe more that local or individuals could invest in. And just curious how that might pan out in our context.
So thank you, Nicole, for a great question. Solar thermal is really a technology that you want to do at scale. There are applications that you can do at home, like solar poiki cookers, but those haven't got too much deployment. It's really solar water heaters that have. I needed to focus in the talk, so I focused on the electricity side because of the awkward chair, but I anticipated a question like this. So this is an example of a trough that's designed to sit on a factory roof. So not something you'd build at your house. This is Francois Rizan's work, who's looking at decarbonizing, in this case, the beverage industry. And these are things that can be built very easily locally and deployed at much smaller scales. So I think a good opportunity there. There are a lot of companies, the economics works. There are a lot of companies that run electric boilers and run off Eskom. There are people using heavy oil and burning diesel. Must be very expensive at the moment. So all of these already, it makes sense to deploy the technology, and this is something that we could very easily kickstart a smaller industry in South Africa.
Thanks, Craig, for the presentation, for the lecture, should I say. You had a slide on lithium battery costs versus thermal costs. And I just got a quick question there. Well, firstly, a comment is that you're comparing thermal energy versus electrical energy. So I think maybe that slide's a little bit misleading. 40% efficiency, maybe the price of thermal should be double. But can you shed some light on maybe how those costs have changed over the past couple of years? I assume that batteries was even more expensive, say, a couple of years ago.
Yeah, so you're very much right, Con. So yes, this is as thermal, and the bar goes up to maybe 50 if you're looking at electricity. So the point is correct, but we're still talking about 4-5 times cheaper. And these are ready with very, very cheap batteries, as we've already got from China. So these are kind of hot off the press figures, and batteries have now come a long way down the cost curve. There's the amounts of I think future cost savings in there is going to that's going to move slowly. Can we give our
Thanks for setting us chair. And I should have thanked you for a brilliant talk, actually. But again, 2 questions. How many hybrid CSPs would it take to run South Africa's energy needs today? And secondly, who's responsible for the egregiously obtuse estimates that are driving South Africa's energy policy?
So I tried to not mention any names when it came to the
You don't have to.
the second question, so I'm going to not put that one on the camera that's going out on YouTube. The first question was, so when I showed that view of what a potential South African grid could look like, I've included 6 gigawatts here. Depending, so this is kind of a least cost option. This uses current CSP costs. If we get somewhere down to what China's doing, there's space for at least 10 gigawatts. So that would be 10 gigawatts, 100.
Thank you for your talk. I think my question was a little bit similar to what I was asking, but I wanted to know on the South African uptick from our maybe different government officials and so forth. Are we engaging with any of them, and what's the uptick of, the results, the outcomes of what we are doing? Is there any investment interest in terms of scaling? Where are we right now?
I think that's a very challenging topic to deal with. There's a lot of reason to pick nuclear if you can drive that investment, and you're sitting there to benefit from it. Whereas CSP is distributed, it's not so easy to get your fingers in that pie. So now I'm getting into those grounds I was trying to avoid. So I think I'll stop there, but I would like to have more influence to answer your question with our decision makers.
Hi, Craig.
Every day.
Quick one. has there been uptake in our neighbors? Because on that on that map that you showed us, Namibia and Botswana have quite a bit of this type of radiation. And yeah, is there any interest in them taking on this?
So Namibia has thought for quite a while on about a CSP plant. They have studied it for a number of years. I know there's CSP people. But I can't remember the figures, but 100 megawatt Redstone plant is a good chunk of their complete electricity needs. So it's not something that they've done, but if we move in the future to a more interconnected continent, then that's certainly an opportunity. And I still think it's a good opportunity for them, as long as they've got connections into, but they're not relying on that one plant for all of their electricity. So you don't want a single point of failure.
Thank you, Prof, for your presentation. Just a silly question on our side. So I'm assuming CSPs use molten salt. In terms of the storage of that molten salt, are corrosive. So what kind of materials then are used to store the molten salt and to get that?
So the particular salt that gets used in the CSP plants is not your conventional table salt. This is what we call a eutectic mix, for those who know all about thermodynamics, but it's a special mix that gets you to a very low the lowest melting point. And these are nitrate salts, not chloride salts. So they're not corrosive. They're actually pretty nice. They're actually, nitrate salts are used as fertilizers. So they're pretty benign. You just have to be careful with them because you don't want to get 565 degrees C anything on you. So as long as you look after that and you keep them safe, they're pretty benign as a storage option.
Good evening, everyone. Craig, congratulations on your inaugural lecture and also for presenting such an engaging lecture to all of us. Colleagues, friends, students, an inaugural lecture always serves as a platform for the faculty and for the university to acknowledge the status and the seniority of an academic colleague joining the professorial rank. It also provides an opportunity for scholars to showcase their academic focus over time. It seems as if Chris has had a very focused career. And the rarity of sharing such an event, not only with your professional peers, but also with family and with friends and with students, truly make an inaugural lecture a special event. Additionally, an inaugural lecture also, of course, facilitates the sharing of insights on contemporary topics. And tonight, Professor McGregor placed the spotlight on an area that touches upon all of our futures and our lives, I dare say. Renewable energy, the incredible resources and capabilities that South Africa have. And Professor McGregor extensively referenced the South Africa sun, the wonderful sunlight that we have here, our industrial capabilities as well as proven technologies of South Africa. However, at the same time, he also highlighted the lost opportunities when decisions do not support investment and growth, and the reality that choices have consequences. Important also, he indicated the need for partnerships, research groups, public and private actors, to finding optimal solutions for society at large, including future generations. There's a very well-known children's poem that you might know by Gareth Lancaster, and the poem asks, "Don't you think the sun is bright? I wonder where it goes at night. Does it sleep or does it hide? Or is the moon its other side? Could it even have a home? Or does it just float around? So the sun goes round and round, spreading sunshine on the ground. A master in his field, Craig, has the ability to enlighten others, also people from the social sciences, like myself, who have little background of this topic. And I think the audience will agree with me that you truly must be a master of your topic, because you enlightened us all. I think all of us understand the concept of CSP much better than we did earlier tonight. I want to say that if all works out, perhaps in a decade, this poem may read, so the sun goes round and round, storing heat and molten salt. To conclude, everyone, in the words of the British historian, Lord Acton, he delivered his inaugural lecture at the University of Cambridge the other day in 1895. Academics such as us, we have the privilege of the sublime art of investigating facts and occurrences, of discerning truth from falsehood and certainty from doubt, in order for our research to strengthen, straighten, and expand the mind. On behalf of our Stellenbosch community, I extend my very best wishes to you, Craig, so that you can continue the practice of this sublime art and also the successful continuation of your academic journey. Congratulations.
Right, colleagues, so I have the honor to say thanks to everyone. So I'm going to make this especially long, since the cocktail will follow after this. So once again, start off with Aqua Power. Thank you very much for the support of the research. Our relationship with Aqua has actually been coming for many years, and this chair of Craig is actually a very, very nice culmination of collaboration we've had with Aqua Power. Then the staff from Corporate Communications and Marketing. Thank you very much, Amira, Chuma, Krista, Jonathan, and Justin. Just to say that I was told Jonathan organizes an inaugural lecture the way he wants to do it. So Jonathan, thank you very much. You're very good at this. The rectorate members, Prof. Smith, Prof. Moyo, and Dr. Retief. So I can also add that Dr. Retief knows our department well, because for many years we've had the honor of being the department that's always late with our marks at the end of the year. Thank you, Ronald, for bearing with us. And then Prof. Mitchley, thanks for that very good question about data centers. It will make sure that engineers will always have work, so please use AI as much as you can. Then from the faculty, Vikas and Christian, it's especially nice because we are also mechanical engineers. It's a very great privilege to actually share this with you tonight. And then all the colleagues from the faculty. As you can see, Craig is very good at cooperation. And if I look across the room tonight, I see colleagues from everywhere in the faculty, and that's very, very special. Then to Craig, thank you. Very nice speech. I could actually follow most of it. And also, Craig, thank you for sharing. I mean, Craig spent many hours in my office and we talk about everything. I must confess, I've sold my Renogen shares now at a massive loss. So Craig's advice didn't help. I wasn't listening. Then last, to the Dean's office staff, thank you very much for doing the final preparations. I'm not allowed, Marley has specifically asked that I don't name them. So Marley, I haven't named them. Thank you very much. And then lastly, if you can just wait while the procession leaves, afterwards you're welcome to join us for cocktail. Thank you very much.